All right, welcome to our video on graphing rational functions, and this is going to be with oblique asymptotes. We've already started graphing rational functions, but we've had horizontal asymptotes, but we haven't graphed anything when the degree in the numerator has been bigger, right? So we're gonna look at that today. Okay, go ahead and start by doing the warm-up. All right, so this is just an example of possible answers. So if you're going to have x-intercepts of -6 and 7, you need to have x plus 6 and x minus 7, or something that's going to give you -6 and 7 as solutions in the numerator when you set them equal to 0. And then n behavior of 2/3 means that there's going to be a horizontal asymptote at y equals 2/3. So I have to have a leading coefficient of 2 in my numerator and 3 in denominator, and that also means that my degrees have to be the same. The degree in the numerator is already x squared, so I made the degree in my denominator x squared. So that's just an example. This one here, and also notice please that I have f of x equals. You could have y equals, whatever equals, but you need to have a function. For B, same idea. There's a bounce point at 5, 0, so that would be your x-intercept that it's bouncing off of, so that's x minus 5 quantity squared. If there's a hole at x minus 1, then you have to have an x minus 1 in your numerator and in your denominator. And then also, if you want an n behavior of y equals 0, the degree in the denominator has to be bigger. So my degree in my numerator was already 3, so I needed to make the degree in the denominator 4. Okay. All right, so as a reminder, I've said a couple of these things already, but when you have a rational function and it's in standard form, the degree in the numerator we'll call m. The degree in the denominator we will call n, and that's in this right here. This is mn, okay? So when we're comparing those two, it tells us whether we have a horizontal asymptote or oblique asymptote. So what you're going to do is you're going to compare the degree of the numerator to the denominator. If the degree in the denominator is bigger, or in other words, n is greater than m, or it's bottom heavy, I say degree in the denominator is bigger, it's automatically y equals 0. If the degree is the same, if m is equal to n, then there is a horizontal asymptote at y equals, and it's a ratio of your leading coefficients. So this would be a over c. And then if it's top heavy, or if the degree in the numerator is bigger, is what I say. If the degree in the numerator is bigger, there's none, meaning no horizontal asymptote. So what that means instead is that there's an oblique asymptote. The oblique asymptote is going to be a line, a slanted line, y equals something, right? And I'll show you today how to find that. Once again, if the degree in the numerator is bigger, there's no horizontal asymptote, there's no oblique asymptote, but only if the degrees differ by one. But that's all that we're going to see today. Okay, if they differ by 2, then there's no horizontal or no oblique asymptote. All right, so what we're going to start with here is it says find the horizontal asymptote of each rational function. So go ahead and try that yourself, because that is stuff that we have already learned. Compare the degrees. The degree is the same, so it's a ratio of your leading coefficients. That's 1 over 1, so y equals 1 when you simplify that. The next one, if you look, the degrees are the same. The degree is both 2 and 2. So it's a ratio of your leading coefficients. 4 divided by 2 is 2, so this is y equals 2. And then this last one right here, the degree in the denominator is bigger, because this is a 2 compared to 1. So if the degree in the denominator is bigger, it's automatically y equals 0. Okay, but now it's what if the degree in the numerator is bigger, which is what we have here, okay? If the degree in the numerator is bigger, you have an oblique asymptote. What we use to find an oblique asymptote is polynomial long division. Now, if you're able to use synthetic division, meaning that you're dividing by a linear binomial with a lead coefficient of 1, okay, and it doesn't have to be a lead coefficient of 1, but preferably, then you can use synthetic division. So if it's a linear binomial without a lead coefficient of 1 or anything higher than a linear binomial, I'm going to use long division, okay? So we want to first off see if there is an oblique asymptote or a horizontal asymptote here. So we're going to compare the degrees. The The degree in the numerator is bigger, so there's no horizontal asymptote. That means there's no oblique asymptote. So let's use polynomial long division to find it. We have 3x cubed. There are 0x squared, so we're going to put a placeholder there. There are 0 linear terms. We're going to put a 0x there, and then plus 2. Divided by x squared minus x minus 7. All right, now we're going to start the process. We're going to look at the first terms, these two right here, and we're going to say, what do we multiply x squared by to get a 3x cubed, which is 3x, and then I'm going to write that above my linear term to stay organized. Then I'm going to multiply this 3x by all three of these terms. So 3x times x squared is 3x cubed. 3x times negative x is negative 3x squared. 3x times negative 7 is negative 21x. And then we are going to subtract this off of that. I like to change it to add the opposite. If you just want to remember to subtract each, that's fine. But I'm going to add the opposite because it makes me feel better. These will always cancel. 0x squared and 3x squared is 3x squared. 0x and 21x is 21x. And then drop your positive 2. Now you're going to start the process over, looking at the first term and the first term, and you're asking yourself, what do you multiply x squared by to get 3x squared, which is 3. And now you're going to continue to multiply out. So 3 times x squared is 3x squared. 3 times negative x is negative 3x. 3 times negative 7 is negative 21. Subtract this off. I don't like subtraction. I change it to add the opposite. These cancel. You have 24x plus 23 is your remainder. Now, for what we're doing right now, we are not going to add the remainder to our answer. Why, you ask? Because we're trying to find the oblique asymptote. The oblique asymptote is what you get right here, okay, when you divide and not including the remainder. Wow, that was hard for me to say. So what you get when you divide, the quotient, and without including the remainder. So it's y equals 3x plus 3. Now you might be asking yourself, why did you continue to divide then? And as soon as you got that 3, why didn't you stop? This tomorrow is going to show us something. Okay, so I wanted to make sure that we were following through. I know right now, no, I'm not going to get into what I know right now, but that does show us something. Okay, but the y equals 3x plus 3 is our oblique asymptote. All right, I didn't do a good job reading the directions. So it says use long division to find the oblique or slant asymptotes. It's called both that, oblique slanted line, right? So slant asymptote. Then sketch a graph of question B. So we're also, for B, going to find the oblique asymptote, but then we're also going to graph it. Wow, I couldn't think of the word graph it. Okay. All right, so since I'm dividing by a linear binomial, I'm going to use synthetic division to get my answer. Why not? All right, so I'm going to use synthetic division. I'm dividing by x minus 1, so I'm going to use synthetic division with a 1. For some reason, my pen's not connecting here. Oh, goodness. Oh, it's because it's on eraser. Smart lady. Hold on. Come on. There you go. Okay. All right, so I'm going to use synthetic division with a 1. I'm synthetically dividing by 1. And then my coefficients are negative 3, negative 1, and 2. And there's no term skipped over. So I'm going to drop my negative 3. Negative 3 times 1 is negative 3. Add those two, that's negative 4. Multiply these two. 1 times negative 4 is negative 4. Add these two, and I get negative 2. Remember, this is my remainder. I was dividing a quadratic, so I'm going to jump down to a linear. So this is 3x minus 4. So y equals, negative 3x minus 4 is my oblique asymptote. Okay? All right, so now we are also going to graph this. And if you wanted to use polynomial long division to check it, you always could. Okay? All right, so let's start by graphing our oblique asymptote. Why not, right? It's here, so y equals negative 3x minus 4. Let's go ahead and graph that. So we have a y-intercept of negative 4, and then a slope of negative 3. I like graphing my asymptotes in red. All right, so I'm going to go down 3, right 1. down 3, right 1, up 3, left 1, up 3, left 1, up 3, left 1, up 3, left 1. And then I'm going to connect these with a dashed line, because remember, asymptotes are dashed lines. Oh, goodness. My arm slipped. Okay. All right, now let's get the other information. All right, so I should see if there are any holes in the graph first, right? So I'm going to see if this is factorable and then if any common factors cancel out. So we have g of x equals, and I'm going to see if my numerator is factorable. So there is a lead coefficient of -1, or sorry, -3. So I'm going to factor a -1 out first. It just makes my brain feel better, but you don't have to. You can just go right ahead and use guess and check, or make your organizational x over x minus 1. All right, and then I'm going to see if this trinomial is factorable. So I'm looking for two numbers that multiply to give me -6 and add to give me 1. So that is factorable, because 3 times -2 is -6, and that adds to 1. Divide by your lead coefficient, which is 3. And then simplify this to 1 over 1. So that's x plus 1 times 3x minus 2. So we have g of x equals, don't forget your -1 that we factored out, x plus 1 times 3x minus 2 over x minus 1. So there is no hole. But I did some work that I needed to do anyways for my x-intercept, so I'm not mad at it. All right, so no holes, none. Doesn't matter the order of anything. I like doing vertical asymptotes next, so x equals 1. Then I will do the x-intercepts. So set each factor with an x in it in the numerator equal to 0 and solve. So that is -1, 0, and 2/3, 0. Y-intercept, plug in 0 for x and see what you get for y. I'm going to go back to the original because it's faster just to do that. That's -2. And then end behavior, there is no horizontal asymptote, so it's not going to follow horizontal asymptote. It's following my slant asymptote, and it's slanted, so it's either going to go towards positive infinity or negative infinity, and I have to graph to figure out which one it is. All right, so let's graph, okay? I'm going to graph my vertical asymptote at x equals 1. Okay. All right, and then now I need to graph any other information. So I have a y-intercept of 0, -2, an x-intercept of -1, 0, and another x-intercept of 2/3, 0. So I'm going to follow my hyperbolic branches, and that's what this piece looks like. Gorgeous. All right, now I need my other piece. So I have, if you look, I have information to the left of this vertical asymptote. I don't have any branches to the right now. So I need to make a table to figure out what that other branch looks like. I could also use the fact that they don't follow in the same direction to help me, but I don't want to make a mistake. Like, I know that it can't go, I'll explain that right now. I know it can't go like this and follow this asymptote of x equals -1, or sorry, x equals +1, because this is not a repeated factor. And I know my end behavior, you'll go in the same direction, your asymptotes, it's if an even multiplicity. But if it's not, then it's going to go in opposite direction. So I know it has to not go follow that asymptote. I know it has to follow this way. So I do know that it goes like that, okay? But if you're unsure, if you're like, what? You could always make a table of values, right? So x comma y, plug in any value to the right of the vertical asymptote. So if I plugged in 2, I get -1 times 2 numbers divided by 1 number. So if I plug in 2 in my numerator, I get 2 plus 1 is 3. 6 minus 2 is 4, so that's a -12. Divided by, plugging in a 2 in the numerator, I get 1. -12 divided by 1 is -12. So I have the point 2, -12, which is down here-ish. And then you can see that, yeah, you get that piece right there. So it's either way, it's up to you. It's not the most beautiful graph. I changed the graph paper from what students look like last year because I actually wanted the numbers on it. But yeah. All right, so now my end behavior as x approaches negative infinity. What does, this was called g of x approach. And then I have to say as x approaches positive infinity, what does g of x approach? So you're gonna look at your graph. Remember your graph is the blue thing. You look to the left and see which direction it's pointing. It's pointing upward. So that's positive infinity. If you look to the right, there's an arrow pointing down. So that is negative infinity. So positive infinity, negative infinity. All right, at this point, you should pause the video and try these on your own. You can then check the answers with my key in Schoology, okay? I will tell you this right now. On the first two here, this and this, I would use synthetic division. If you want to use long division, you can, but I would use synthetic division. On these two, you have to use long division, okay? And then on this one, it's just practice graphing once again, and it does have an oblique asymptote. So you can try those on your own and then check it with the answer key.